I think it's cool.
What's the requirements for each one? So you have 4 here, have to do 4 things. How many things you have to do in this and that? There's a lot of data showing you how to do it, but we have to figure out how to send the files and receive it. That's for TCPs. For UCCS, that's it. You have to drop something and package with purpose. So we have to figure out how to. I didn't realize that was the same. You know,
Yeah, it's kind of.
you have to drop it for the UDB. So we have to drop it purpose.
For a lot
Then
of
we
different
figure out how to drop,
I have a buddy that's
plus how to log that drop back and switch back and forth.
yeah, it's like the general understanding that, you know, where you know, like forward first and all that stuff.
What?
It makes me laugh so much.
Yeah, I didn't know what that plantation, Shibano, and Linda. What else?
Yeah. Here I'm Steve.
And he uses one.
That'll work. No. What's that? I can't tell you. No, I'm just kidding. I'm at Peter, so sorry. Actually, don't worry.
We got that.
Sorry.
One quick question, sir. Regarding the project,
Yeah.
do we have to bring up 3 Linux servers, right?
Yeah.
And
So you can do it, honestly, the servers are there for people that don't have access to like OS 10 or Linux on their machine, be it it's either native or a virtual machine. That is honestly easier. So I'm going to provide access to those machines because some people will want it anyway. It will be way easier to do your project on your own machine. Way easier.
so we can use our own machine and just
Sure.
bring up the.
Yeah, just do it in so that the Unix stuff works. So VirtualBox or whatever.
Do you have a preferred flavor of Linux?
It's going to be, it should compile everything.
Okay.
It's because it's not going to be overly complicated. If you looked at the shells, right, they're like 25 lines long, right, and you just stuff your own stuff in there. So.
Great. Thank you.
Okay, so we talked about Classic Ethernet. Classic Ethernet is the old style Ethernet, right, with the coax cable and the vampire taps and all that. So we're going to move on to something more modern, right? And we're actually going to talk about basically switched Ethernet, which is what we have today, right? Switched Ethernet. So ironically, switched Ethernet actually removes a lot of these problems that we've been studying. So if you have a network, we've been drawing networks like this, right? Right, and the problem with this network is as we discussed, the computer A wants to talk to computer C, then they send out a frame. If the frame is short, right, they can send them out at the same time and they collide somewhere in the middle. Everybody hears all the collisions. And then we discussed, well, if we made our frame bigger, then we'd be able to have it completely across the frame before it got there, and so on and so forth. So a switched Ethernet hooks into a switch. So in reality, a switch makes it to where every network on the entire Ethernet is simply a pair of two computers. There is no collisions because the what enters in into the switch is destined for only that direction. And we're on Ethernet cable, so we have two different wires to send it across. Actually, two different pairs of wires to send it across. And then we have some other wires that we're going to use for gigabit later. But the idea is there, right? So when you go into the switch, there is no, it's virtually like two computers talking to each other. And two computers talking to each other, particularly if they are not simplex, but they can talk down both wires, right? Then there is no collisions, right? And then even better, we could build in some of the stuff that we do with collisions where the frames actually span the entire length of the network, and then we can use both wires to communicate at the same time. So, how does switches work? So first, let's talk about the old thing that you mistakenly bought on Amazon again, called a hub. Looks surprisingly like a switch. It is not a switch. What do you think a hub does?
Makes trouble.
It definitely does that.
Regenerate signals.
Huh?
Regenerate signals.
So it does, most of them do act as a repeater. But in simplicity, like if you had a pair of wires coming from A, and we'll just do pairs rather than pairs of pairs and so on and so forth, right? In simplicity, we have one here, then we have one here. A hub simply takes this wire, wires it together with that wire, wires it together with that wire, right? And they wire it together. So like you were wiring your house for electricity.
So it's kind of like a mesh network.
Yeah, yeah. So what this essentially becomes is a classic Ethernet that spiders out, right? The vampire taps are really long, right? We could have a classic Ethernet cable, and then one computer is here, one computer is here, one computer is over here, right? And we just vampire tap it like that, right? That's what a hub looks like. Where this little vampire tap, right, is part of the length of the network. So they cause trouble, right? And so don't mistakenly buy those out on eBay or Amazon. So the question is, what does a switch do? And I'm going to draw this with only 4 ports, because you will get the idea why we're not going to do any ports here in a second. How does a switch work?
To like physically switch connections eventually.
Yes. So inside of a switch, so imagine these are the wires coming through, right? There is a fabric. And the fabric has, you can think of them as like relays, right? Or if you really want to get down to what a relay is, right? They're stoplights or direction signals, right? And if you have a fabric inside of here, then you can see that we could be able to route from this port to this port, right? And we could route from this port to this port again without ever crossing wires. So then a 16-port switch has a 16 by 16 fabric inside. So this allows us to connect to the switch, and the switch exists at the network layer. So at the, or not the network layer, the link layer, right? Not the physical. A hub is a physical layer device. A switch is a link layer device because it actually looks at the addressing to figure out which stoplights to turn on and off inside, or which relays to turn on and off inside, so that that things can be routed to the right port.
You said hub was like a transport layer?
No, it's at the link layer.
Link layer.
Yeah, link layer.
The hub.
No, that's the physical layer.
Okay, the
It's
physical.
literally like wired together. Trouble.
So for this one, it should be 4x4, right? So we should have like 16 fabrics, right?
Yeah, there should be 16 nodes
Okay.
inside the fabric. Right, whereas 16 by 16 we have 256 nodes, which you can see why a 16 port switch is so much more expensive than an 8 port or a 4 port, right? Because it's an exponential growth of the fabric inside of there. So, how do we make this work?
I have a question.
Sure.
Could you tell me the pathway of how a switch would allow the connection to go through different nodes?
So we do addressing. So this is port 1, port 2, port 3.4. We have a little table lookup over here for so 1, 2, 3, 4, and then we have addresses here. So really what's actually connected to this stupid thing. So if this is computer A, this is computer B, C, and D, then it maps those to A, B, C, and D. And then when D wants to talk to A, so information comes in on port 4, right? It comes in on port 4, so it says, I want to talk to A. So it goes to the table, looks up A, says, oh, that's on port 1, and then routes it over here. That's all that really happens. And a switch literally is not all that complicated of a device, except for what happens if B, C, and D want to talk to A all at the same time. Remember, these things are being utilized at 100%. Right? The wires are saturated when they send. So what happens if you send to B, C, and D all send A at the same time?
So like internal queuing maybe?
Yeah, so now we need to build in like queuing, right? An input and output buffer so that we can queue these things up in there. Eventually you can overcome the buffer. However, since network traffic is often bursty, that means that we can use some things like statistical multiplexing we did before, where we say, oh, you know, a computer usually only sends this amount of traffic, how much buffer size do we need, right? Now, what are some of the advantages of a switch?
Create separate broadcast domains.
Oh, yes. Create separate broadcast domains. Remember, this is all at the link layer, so we're not dealing with IPs or anything, right? So it's not routed yet. We're gonna get to that later.
And no
Right.
collision.
Huh?
No collision.
No collision. There is no collision on a switch. We need no collision detection at all. In fact, modern Ethernet has no collision detection built into it. Because if I was talking directly, we have a line and we're talking directly to each other, then we should be able to do that without ever stepping on each other. Right? It's only when you start adding 3, 4, 10, 20, 50 parties into our conversation that it becomes a problem. And remember that the switch buffers for us. So even if we're talking to 2, the switch will gather the packets, store it in short-term memory, and then forward it when the line's free. And the switch knows when the line's free because it's in control of it. But it does create some other problems. So in our very classic Ethernet, it was simple, right? We had one wire that snaked through the building, right? And we connected computers to it. Now we don't have one wire that goes through the building, right? we have wires that normally go to some kind of wiring closet, right, with many ports, right? And then switches stuck somewhere in there or in other racks that go into these ports, right? So on and so forth. So rather than the wiring closet layout, right, really what it looks like is we have switches that look like this. And we have a group of computers attached to this thing, a group of computers attached to this thing, maybe a computer attached there in the core, a group of computers attached to this thing, group attached to this thing, and then switches that are interconnected. So if switches are interconnected, how does this computer over here, X, Y, and Z, right? X, Y, and Z can easily communicate to each other because this switch is connected to these three computers. And we have that very simple table that we had up on the board, right? But what if computer X wants to talk to one of these computers over here, A, B, and C? How does it know who to talk to?
Something's gotta like translate.
Has a request for ARP, like say.
So what we are describing is ARP, right? So this is ARP, but you know, we can simply say, oh, that's an ARP packet, or we can actually describe how it works, right? Because we're gonna design these things. So if we're designing these things, if computer X wants to talk to computer A and it's not on this hub, what do we do?
Send out a request looking for that
We
address.
send an ARP to everybody. We say, hey, we broadcast on our network, right? And send an ARP to every single port. One of those ports has to be this one, because we send it to all of them, except for ourselves, right? So one of the ports it has to be that one, right? Y and Z also get it, right? But when we do that, right, we'll start building tables, and then when we start sending out broadcasts, we won't have to send it to everybody, because we can start building complex tables. So X wants to talk to A, so it sends out a broadcast, right? And then so one of the broadcasts makes it to this switch. What does that switch do?
Rebroadcast.
It rebroadcasts, right? So we send out a broadcast, and it makes one of them. It makes it out all these ports, but one of the ports is that one, right? And then the same thing happens here. So let's say this is a brand new network, because if it had already been talking to the switch, it already knows where to go, right? So it gets out there, it gets to A, right? So we send a message to A. Normally, when we send messages to computers, we expect a response. You know, we just don't send out messages, we expect responses, right? So A sends out a response. Well, so let's take a look at what happened in this table, right? So this is port 1, 2, 3, and 4. So again, we have 1, 2, 3, and 4. And on port 1, we have X, right? And then on, and so A sent out the packet, so this one now knows that this is X, right? Then we have the same thing over here, right? 1, 2, 3, and 4. This is why we're doing 4-port switches, but you can see that it would expand to all of them. So we have 4 ports over here. Let's say this is 1, 2, 3, and 4. So 1 receives a packet, right? Well, who does it come from?
Comes from one.
That switch.
It did come from the switch, but whose address is in it?
X.
X. So it says port 1 is X. Now we can have multiple values in there, right? But port 1 is X, for sure, right? So then it broadcasts out, right? And then we have like this. And let's say this is 1, 2, 3, and 4. So now we get a packet from 4 and it's also X. Right, and then we get it to A replies. So now we say, oh, 1 is A. It has something going to X. So we don't broadcast it anymore, we send it out this port. It comes into this switch, it says, I know where X is, and I send it out this port. Right? By the way, we also learned that port 3 is A. And then it comes out this port and goes into port 4. Port 4 says, oh, I know where X is, it's 1, and it delivers the packet. Now we have a route through the network that X and A can talk to each other. No longer have to broadcast. So then, let's say that A wants to talk to Y. So A wants to talk to Y. We do the same thing, and it goes through the network the same way, right? We broadcast, broadcast, broadcast. We finally get down to Y. Y is on port 2, right? And we already know that A, or we'll just put it there. A is on port 4, so we just go back out port 4, and all the switches know to talk to A. And well, on the way back, all Y gets put into the right ports, right? So Y comes in from port 4, and we just, oh, that's sorry, that's 1. So Y is also on 1. And we build these lookup tables with multiple values in them. And we can simply get around it. Now, this is a simple network. And we started talking about this on Wednesday. What happens if you're building a network and this is starting to become into things that people have experienced in class? What's wrong with this one?
Bad news.
It's bad news in what we
all
just...
broadcasts just start spinning.
Yes, this is called an ARP storm, right? So older switches, right, when you connected them together, the first broadcast, the very first one, never reaches an end because it keeps rebroadcasting, rebroadcasting, rebroadcasting. And it doesn't have to be this simple loop, right? It could be something like, maybe you have a redundant switch in the middle, right? It's not unusual to have a redundant switch. So you have a redundant switch just in case something goes out, and then you buy a cheap one off of Amazon or eBay or somewhere, and it's old, and you stick it in there, and it has zero idea what to do with broadcast messages on how to negotiate this. So let's say, again, there's some computer, rather than drying out the computers, there's some computer on this switch that wants to talk to some computer on this, right? So we get a broadcast, right? Sends out all ports. It goes to the computers also, but that's unimportant at the moment. So it goes to this switch and this switch, right? This switch does what? It sends out this one and that one. What's this switch do?
Sends it out its 2 ports.
It sends it out this one and that one. Right? Now we get this switch and this switch, right? Again, so we get another one down here, and then this one goes this way. Right? And these are isolated. But you can see that we're going to get this, and it's going to start flooding the whole loop with ARP packets. And it will shut down your network really, really fast. Because all the advantages of switching just disappeared, right? Because we're no longer have a single path to a computer. We have multiple paths to a computer. and those multiple paths start reacting to each other. So how do we fix this?
Spanning tree.
Yes, this is spanning tree. So this is an interesting algorithm because it's actually really simple. But when you first think about it, it seems extremely difficult. So we want to create a network that is completely decentralized. We don't want any management services because part of the beauty of Ethernet is that we can just plug and go, right? We don't have to have a managed service picking which switch is in charge. So if we have a fully distributed network, how do we negotiate who is in a spanning tree? What we would really like, by the way, when we say spanning tree, is we have a number of points. We want one path through the network. With no loops. For right now, we don't care what that path is. It's important that we only have one. So how do we negotiate if everybody on the network is completely decentralized and there's no person to say, hey, I'm going to be the root of the network? So it seems like a really hard thing to solve. How do you have 6, 7, 8 different devices running the same algorithm decide what path to go through the network, all independently of each other? You could do shortest path, right? And we actually are going to do shortest path. Sorta, you'll find that it's not always the shortest path. But the question here is sometimes, like to get to, this might not be a great diagram. Sometimes to get to 2 different nodes, right, the paths are even. Then how do you pick?
Then you have to just like randomly choose which one.
You can arbitrarily choose, but if you arbitrarily choose, then you have to tell somebody else to make the same choice. So, but you can make a not arbitrary choice. You can decide on some measurement, and that measurement is completely irrelevant, so long as both devices choose the same thing. So it is arbitrary in that standpoint. And so what you do is, the way to get around things that are the same length is you say, hey, what's your MAC address? And if you have a path that is the same length, the lowest MAC address wins. And if the lowest MAC address wins, because those are hard-coded into the switch, then we now have a independent measurement. It's arbitrary, doesn't really matter, but it's an independent measurement that both algorithms will decide that win.
So in this case, are we talking about connectionless network, or we're talking about connection-oriented network?
So we're not talking about either one yet, because the connection and connectionless and connected is in the network layer.
Oh, okay, because I was just thinking that.
We're just moving packets across the network. No IPs, nothing. So a Ethernet doesn't require IPs. So if you're doing like Wireshark, you'll see something that says, hey, who has 192.168.0.1, right? And what responds? The switch does, because we put some circuitry in there to say, instead of routing this all the way across the network, like the switch lies and says, I'm that person, right? Because it will get it and it will route it the right direction. So let's run through a spanning tree. And then we're gonna move on to some problems. All right, so let's do a little simpler one. All right, we have a network that looks like this. Little simplistic, but not totally unrealistic, right? We have two core switches in the middle, and they are connected like this. What's actually even worse than that? Two lines between them. Let's make it really bad. So we could arbitrarily design, if we were going to centralize work this network, we could arbitrarily say, we can fix these loops, right? We can kill this one. We can even kill that one. Or did I take care of, no, I gotta kill this one. Or this one, doesn't really matter. Right, we could take all the loops out of the network. And notice the network can still fully communicate to each other, right? Some might be some oblong routes, right? This one's nice and direct. But if I wanted to get to this one over here, I go through this one, and then to this one, and then back up. We could arbitrarily do that. But we want to decentralize. So what we're going to do is set up a very simplistic algorithm. So the initial state of the algorithm is every switch believes it's the root. And so I'm going to label these A, B, C, D, I believe E and F. And let's just for the moment pretend that these are MAC addresses. MAC addresses are much longer, right, because they need to be unique. But let's pretend that they're MAC addresses, and we know what the order of A, B, C, D, and F, E, and F is. So, the first thing is every switch starts off believing it is the root. So A sends out a frame that says, "Hey, I am the I am the root, and the root is 0 hops from me because it's itself." All the other ones do also. So B says, "Hey, I'm B. B is the root. I am 0 hops from myself." C, D, E, and F all do the same. So, which ones receive those messages, right? These are not broadcast messages. They don't get rebroadcast out. So they arrive at a switch and then they stop. So C receives, "Hey, this is A. A is the root and it's 0 hops from me." So C says, "No longer the root," right? So C updates to, "Hey, I am C. A is the root. It is 1 hop from me."
So the length cost between C and A is 1.
Huh? Yeah, this one right here. It's 1 hop, right?
Oh, okay. Sorry.
So because B is not connected directly to A, it doesn't receive any message from A. So B gets a message from F, B wins. Gets a message from C, B wins. So B still believes it's the root. So if we look at this in like a table format, after the first round, everybody's, so let's call this 0th, right? Everybody believes they're the root. A, 0, B, 0, so on and so forth, down to F, 0, right? And then we go to the first round of actually updating. And then we have A, 0, and we have B, 0, and we have C, A, 1, right? What is D? No, it wouldn't be F because the D would win over
The
F.
lower.
So it's always lower.
DC,
So
DC1.
yes, it is DC1. And it's DC1 because the first round, this hasn't been sent out for the new update yet, right? So it receives CC0, so D believes that now D C1, and E is what?
EA1.
E is A1, and F is what? FB1. Then we go to our second round. So what does A become? Well, you can tell A is going to be the root, right? A 0, that's a foregone conclusion at this point. Right, and then we have B, C, D, E, and F. And what are those?
BA2, CA1.
Yes. BA2,
DA2,
CA1, DA2,
EA1,
EA1, and then FB1. B1.
So one question.
Uh-huh.
Why can't F receive from D or E receive from D at the same time as E receiving from A and F receiving from B, since they are all connected?
So there are other algorithms that exist beyond spanning tree, right? Because you're going to see, we're going to get a route through the network where A, who's on the edge, becomes the root, is non-optimal. Obviously, the shortest distance from a field is the center of that field, right? So optimally, it should be one of these two that is the root for shortest path, right? But in designing, this was a real problem, right? And it's been like people in this room were already in IT, not including me, right? That actually dealt with this problem because it was newly being propagated. It actually got solved in, oh gosh, right there, doesn't have the date, but it was solved by, I believe, Digital Equipment, right? So, I mean, it was a while ago, but even just because we solve something, right? For those that are going to go on to your PhD, you'll solve something, and you won't see it in the industry for like 6-7 years. Because it just takes time for the business case to get built up and technology to get cheaper and you know, productization to happen to actually move to a market. So this was actually a real problem 15 years ago, right? So we're actually into modern times. And then there was better solutions, right? So there are more complex solutions, but this is the baseline of how you can do something that is completely distributed, doesn't rely on anybody. So if you guys want to go down the third round, what do you think the third round is?
anything but F, no.
Yeah, does F,
A3.
does F become A3 or A2?
A3, V.
Okay.
Any other updates? Or two, actually. Oh, no. B gets updated. V is C. D actually gets updated too, but it's the same.
In the second round, how did we know that it was A?
Oh yeah, we in the second round we don't know yet.
That's CA1.
No, yeah. B updates to BA2 via C. Yeah. It gets this one message right here. It's just, I think it's okay. And then B actually gets the same message via F in the third round, but it's stupid, so it doesn't change. The only thing that actually changes is this one.
How does it know when it's done? It'll just keep going.
Because it will send out a message and there'll be no updates.
Okay.
So, and the spanning tree is obviously a discovery process, right? So when you add a new, it can't happen from a computer. So, because unless you are running two NIC cards in there, you're purposely put drivers in there to do routing, then there should be no loop via computer, right? So this is totally a switch thing. So it only needs to be done when a new switch is added to the network or something dies, right? So you can simply have a discovery process, and when the steady state has been reached, you just simply turn it off.
So this example we did in class with rounds, this is assuming what, that they're all chirping your discovery process at the exact same time, basically.
So once the discovery process, so for instance, let's take a new switch, right? It's easy to start the discovery process because you put a new switch and you turn it on and it says, hey, I'm a new switch. Let's start spanning tree. And all the switches go, all right, right? Because it broadcasts out and then they start doing it. Falls to a steady state, and then once the steady state's been reached, they turn it off. And then unless something dies, like, hey, I've been forwarding, so on my, now you actually have a path through this network, right, where A is the root. Right, it kills this one. Oh, this is an interesting case here, C and D. Right, how do you pick which one? They have a loop between each other. So how do you pick?
Lowest port.
Lowest port. Right, same way you pick the other things. Now you just pick lowest port. Right, so you turn that one off. The wire's still there, but you turn it off, right? And so on and so forth. And then if A starts trying to talk to F, which goes through C, right, and it says, hey, I've been trying to talk to F and he's not responding. And then, hey, I tried to talk to C and it's not responding. C is in my path, so C must be dead. Is there another way around the network? Right, in this case, there's not. Well, actually there is, because you could talk to E, get to D, and talk to F. Right, so you start spanning tree again, take C out of the equation, and makes a new tree.
And so as they're going in this scenario, it's shutting off the ports. that
Yeah,
are
it
losing.
is.
Okay, so that's
Yeah.
the part I was gonna say, shutting off the ports that are losing every round.
Yep.
Okay. Because I was trying to figure out how we avoid the intermediate states and some of the other stuff that may happen.
So once that you shut off ports, once steady state's been agreed upon, and then you shut them off.
So what if you insert a new switch after steady state's been agreed upon?
It'll say, hey, I'm a new switch, let's start spanning tree.
Oh, okay.
Cause won't it immediately say I'm root? And
Yeah,
I
yeah.
pass that to
Oh, by the
everybody?
way, I'm root. Everybody else is like, I'm root. Right, and we start the whole thing over again. The easy case is adding a switch. The harder case is what happens if one quits working, or somebody unplugged it, or it was switched out, right? It's now missing in the network. Right, that means it can't update the network that is there, so other things that were connected to it need to notify that we need to start spanning tree again, because I can't communicate to blah, blah, blah. And that, other than there are some much more advanced algorithms, rather than the spanning tree. The spanning tree works, and for the basis of this class, I mean, you could think of, in fact, some of your, I think there's a paper in that big list of papers that talk about how to make highly efficient networks. Because there could be some other things in there, right? What if these, you know, if these were 40 gig core switches, right? You probably want those to be root, right? If A is 100 gig and this is 1 gig, right? There's other decisions that can be made to make it better. Or 100 meg, not 100 gig. But you get the idea. All right, now let's go through some questions.
One
Go ahead.
question about the switches.
Mhm.
So the learning, is it gonna be like a save forever? Just my concern is, what if we have like a compromised switch and just changing the whole calculations? So that will cause a loop.
What if you have a, so there's a joke, like when you go to operator school, right? If you can't compromise a router in the first day, they kick you out. Routers are generally, and it could be managed switches too, it doesn't have to be a router, right? They are very vulnerable points in the network. And things that are software updatable, like you have a high-end Cisco switch, then you can really mess with things. Really mess with things. Because the switch, ironically, the switch that you buy off of Amazon for $25 is way safer to use, maybe not as efficient, but it's way safer to use than a Cisco iOS switch. Because the Cisco iOS, you can change. That one that you got off Amazon is all hard-coded. There's usually not even a way to update the firmware. You can't change anything in it. It's built.
Not with that attitude.
Yeah, not with that attitude. Exactly.
Do we have to memorize how we got the results for these?
So I might put spanning tree on the test. But if it will not be any more complex than this. And it might be less complex than this. We'll see. The idea is if you just keep it in your, if it's a fairly simple network, you just keep the tables and you're safe. All right, so, you know, this is the first round, this is updating, so this becomes the packet that gets sent in the next round, right? And so then you just update the tables. All right. Does anybody have the list of problems they sent out for?
Yeah, 3.1.
So it's 3, 1.
This was problem 1, 6, 9, in chapter 3.
Okay, 1, 6, and 9.
And then
He's
2
a one.
and 6 in chapter 4.
All right. time I'm up here and flipping through the book, I feel like I should get preachy at the pulpit. Hate teaching from the pulpit. Let's see. All right, problem 1. An upper layer packet is split into 10 frames, each of which has an 80% chance of arriving undamaged. If no error control is done by the data link protocol, this is what happens if we don't do all the work that we've been studying for the last 2 weeks. How many times must the message be sent on average to get the entire thing through? What's our facts?
10 frames.
10 frames, right?
80% each.
Yeah, 10 frames. And 80% chance of getting through each, right? This is 80% positive, right? If we make the 80%, we made it. Not 80% negative, right? So 80% each. So what's the odds? It's 0.8 to the 10th power. Yeah, 10%-ish. Exactly, yep, 0.107. So if it takes 0.107, on average, how many transmissions? It's, yeah, we just invert it, right? So it's 0.107, and then we invert that, and it's somewhere around 9.3 times on average.
I would kind of think it would be half of that, but I guess my math was wrong.
Yeah, 9.3 on average. So sometimes it will take, it's a probability, sometimes it will take more, sometimes take less, but if you did it many, many times, you would converge on 9.3. All right, question number 6. I'm gonna put one of these, I'm pretty sure, on the test because it's super easy. And everybody should have like that relief question.
We have 6, 5.
So, question 6, a bit string of many ugly ones. Let's read this out. This would be much easier on the test because you don't have to copy anything. 0, 1.
Then 5, 4 ones.
1 and 0, then 5 1 and 0, then 6 1.
5 ones. 6 ones. 0.
All right, we're gonna bit stuff this thing. What's the rules for bit stuffing?
So after every 5 1, add a 0.
If for every 5 ones, add a 0. Is there 5 ones here? No. Is there 5 ones here?
Yes.
Yes. Do we add a 0?
Yeah.
Yes. Is there 5 ones here?
Yep.
Yes.
There's 6, right? Where do we put the 0? Ta-da. Done. And if this question was on the test, I would accept it just like this. Because I don't want to read how many ones you put down. I would like to just see, oh, these are the 2 zeros I stick in. And they might be spaced apart so that you can put a 0 there. All right. Number 9. 16-bit messages are transmitted using a Hamming code. How many check bits are needed to ensure the receiver can detect and correct single-bit errors? This first part of the question. 5 Wi-Fi.
And 1, 2, 4, 8, 16. And also
Yeah,
the
the 16 is in order to represent 16, right? We have 2 to the what? 4. So this represents nothing in Hamming code, right?
Mhm.
And then this represents nothing in the Hamming code. And then we finally get 1, right? To the 4. And then what do we get? And then what do we have here?
54, 8.
That's 3 now, 3, 1.
Oh, sorry, this is 3. Right. So we have to the 4th there, right? So we really just count out how many bits we need to store. And remember, in order to store that last bit, right, we have to have a Hamming digit for that. And the Hamming digit for that is you need a position for 1, 2, 4, 8, and 16, which should be over here. Somewhere. And then we can store how many bits with that? We can actually store more. We store right up, we store as many bits right up to the thing before what? To the 6th. So we can actually store 31 in there.
Why is it 6? That's
Huh?
that's the maximum? you can
No, no,
store?
no, we can keep going. Yeah, no, we could, if you wanted to store more, but you just have to have more Hamming codes, right?
Mhm.
So the next part of the question is, how many show a bit pattern transmitted for a message 1101. Yeah, you gotta read this to me again. What is it? 1101 0011, like that?
Yeah. 0011. Another 0.
Okay.
Oh, 0011 again?
Yeah.
Figure out where that is, right?
And then English word for person.
So this is position 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So
Tell myself phone numbers.
Yeah.
0101 again.
So that one's over 1.
and then we have right here, or to the 5th,
Yeah,
right?
that is 0101.
Another 0101?
Yeah, it's the last one.
Alright. 0101, like that? Alright. The first one's super easy. Why is this super easy? Because it's simply all odd numbers, right? What does 2 equal? It's everything that has 2 in the, and remember we have 0, 1, 0, 0, and these are question marks. And we have 5 of them this time. So it's everything that has 2 in the bit. What are those numbers? 3, 4.
You flipped your last heading, your last paragraph was like the parity bit and then 10101 at the end, I think. Cause the parity bit should be the 16th bit, right?
Yeah, it should be there, I might have screwed up. We'll look when we get there. So what's our numbers for 2? It's 2, obviously, but we don't use that. And then it's 3. Is it 4?
No.
No. It's what? 3, 5, 6 and 7. And then
10,
so let's just go through them. So 3 is 2 and 1, 4 is just 4, 5 or 4 is just 4. 5 is a 4 and a 1, right? So not 5. 6 is 4 and a 2, so definitely 6. 7 is a 4, a 2, and a 1, so definitely 7. 8 is out because it's perfect. 9 is an 8 and a 1, right? 10. 10 is an 8 and a 2. 11. 12. 13. 14. 8, 4, 2. 15. 16. Okay, perfect, right? 17. 16, 1, 18. 19. 20. And 21? 22. 22, right?
But we don't have that, right?
So the 20, should stop to 20.
Yeah, it stopped at 20, so we don't need that. And then the 3, and then the 4, and then the 5, right? Or I guess let's do the 4, the 8, and the 16. So it's not all that hard, other than writing the stupid tables. After we write the table, let's just do the 1. What is the parity for 2? Right? It's everything in 3, 6, 7, 10, 11, 14, 15, 18, and 19. So 3 is yes. 6 is still yes because it hasn't changed. 7 now becomes no. 10 becomes no because that doesn't change. 11 becomes yes. 14 becomes, I think it's over here, no. 15 becomes yes.
I think you're off by 1 there.
Yeah, a better table. So it's not all that hard, and anything on the test will not include this stupid thing. In fact, maybe we ought to just cut, maybe I'll do something like this. Right, so there is some 2 to the 4 of it. Somebody ought to invent a machine that can calculate these things. All right. Two and 6, right? A group of N stations share a 56 kilobit per second pure Aloha channel. Pure Aloha. Each station outputs a 1,000 bit frame on average once every 100 seconds, even if the previous one has not yet been set. Examples, the stations can buffer ongoing frames. What is the maximum value of N? How many stations can we have? So Pure Aloha network, it's key, has an efficiency of what?
18%.
Yeah, it's about 18%. And the book says it's 18.4 if you really read it. But if you did 18, it'd be right. And so, and then what's our data?
56.
56 kilobits, right? So we have a 56 kilobit channel times what? So this is a percentage, right? So let's get rid of that, put the decimal point where it belongs. So 0.184 times 56 equals what?
10.3.
10.3. Now the next part of our question. We output a 1,000 bit frame on average once every 100 seconds. What does that really mean?
So every second we have 10 bit frame.
Yeah. So it's simply, we have 100 seconds, and every 100 seconds we need to transmit 1,000 bits, right? So we need 10 bits per second. So we transmit 1,000 bits every 10 seconds, right? Which gives, or 100 seconds, sorry. Which gives us 10 bits, ironically, per second, right? So if we have 10 bits per second, how many stations can we get? So we had 10.3 kilobits per second, right? So 10.3 thousand bits per second. And we need what?
10 per second.
We need 10 per second, so let's just do this. Oop, one too many zeros. Divide by 10, and that gives us what? 1,030. Number 6, what is the length of contention slot in carrier sense multiple axis collision detection for a 2 kilometer twin lead cable? Twin, I guess it's twin lead. I wonder if you get hazmat for that. And then B, the same for a 40 kilometer multi-mode fiber. It gives you some propagation times. And it tries not to give you a hint what the propagation times are. What are the propagation times usually measured in for fiber and wire, and everything for that matter? It's the speed of light, right? It doesn't mention that in there. It just says 82% of signal propagation in a vacuum, but the vacuum should be a hint, right, that you're comparing to something at the speed of light. So we have 82% the speed of light for the first one. So 82% the speed of light is what? 2.46 times 10 to the 8th meters per second. The signal propagation time for 2 kilometers of cable is what? How long is, at this speed, how long does it take to get across 2 kilometers of cable?
2,000 meters divided by that. So, 8 microseconds.
Yeah, it's right at 8 microseconds, right? It's, the book says 8.13, but it's basically 8 microseconds. The trick here is,
Twice that.
is twice that. Why is it twice that?
Back and forth.
Because I mean, they can like start transmitting at like the very, very end.
Correct. Remember, what they're really asking here is they're throwing a bunch of numbers at you, but they're really asking you to remember that to do this, you have to have twice the length.
Can you repeat that one more time? I'm sorry.
So remember back when we were talking about contention and that you had to fill, right? I drew a picture just like this, and you had to fill this thing up so that the packet went the whole width of the network, right? And this is our packet size, but in order to do contention free, if it collides, then the collision could have happened right at the end. Right, and so in order for this guy to hear the collision, it has to be double the length. You have to get it back down. So that's why it's always 2 times the distance. And so it's the same thing down multi-mode fiber, right? It's the same problem, different numbers. And we can just leave that up for practice if you want. Right. Now it's 40 kilometers and it's a little bit faster because it's fiber, but it's the same problem. Just remember, you gotta go double.